Between 1968 and 1972, America launched 9 human missions to the moon, 6 of which successfully touched down, allowing 12 men to walk on the lunar surface. NASA's next chapter of lunar exploration, called Artemis, has the task of not just going to the moon to create a long-term human presence on and around it, but also to prepare for ever more complex human missions to Mars. In short, everything we must be able to do here, we must first do here. So, what will an Artemis mission look like? Everything is designed and tested with our most important element in mind, the astronauts. This is their deep space, human-rated spacecraft called Orion, built in 3 parts. The crew module, where up to 4 astronauts will live and work throughout the flight. The service module, with life support systems for the crew and its own engine and fuel reserves. And a launch abort system, with engines capable of pulling the crew module to safety during launch should anything go wrong. To accomplish the task of launching our crew and heavy payloads, NASA is building the Space Launch System, comprising of a cargo hold, an exploration upper stage, a massive core stage, and 2 extended solid rocket boosters. Altogether, this is the world's most powerful rocket, and it exceeds the legendary Saturn V of the Apollo era in numerous ways. Sitting on the launch pad, the entire rocket, fully fueled, weighs just over 6 million pounds, 5.2 million of which is just the fuel. Once ignited, there is no stopping what comes next. All 4 RS-25 engines and the 2 solid rocket boosters come to life, thundering our crew upwards. 2 minutes after ignition, the solid rocket boosters are spent and released. 8 minutes after launch, the core stage is depleted and separated. The upper stage fires briefly, placing Orion into a parking orbit around the Earth. Here, the crew reconfigure the spacecraft and check systems to confirm everything is ready for deep space travel. With a go from mission control, the crew reignite the exploration upper stage engines to leave Earth entirely. The exact timing of this maneuver is critical to reach a speed that can escape Earth's gravitational pull, but also put Orion on a course that will intersect the moon days later. Once this burn is complete, the upper stage of the SLS is jettisoned and the crew aboard Orion coast for several days toward all that awaits them at the moon. Approaching the moon, we see the fundamental differences between Artemis and Apollo. Instead of requiring Orion to serve as an expendable lunar command module or to carry a constrained lunar lander, the Artemis missions will take advantage of a different approach: pre-staging. Everything needed for lunar missions will be positioned in advance by commercial and international partners. This includes rovers, science experiments, and human-rated systems on the surface. But it also includes a dedicated lunar station in orbit around the moon called Gateway. Here at this station, we can pre-stage a robust lunar lander and establish a strong communications relay. Designed with open standards, the Gateway can be expanded as new missions and partnerships develop, allowing multiple human missions on the moon at the same time and enabling ongoing science to be conducted even between human missions. The Gateway is also capable of adjusting its orbit to allow access to every part of the moon, something the Apollo missions could not do. But the real key in this approach is placing Gateway in a unique halo orbit to perfect the maneuvers needed for Mars missions. And with the growing list of commercial and international opportunities, Gateway is the ideal hub between Earth and all that lies beyond. Returning to our crew as they approach Gateway, the Orion must match the elliptical orbit of the station in order to successfully dock. Once on board, pre-selected crew members transfer to the lunar lander, while those assigned to Gateway remain on station. The lunar lander system itself is built for 3 unique steps: descending from the halo orbit of Gateway down to a low lunar orbit, descending from low lunar orbit to the surface, and once the lunar mission is complete, launching from the surface of the Moon and ascending all the way back to the orbiting Gateway. Once back aboard the Orion spacecraft and undocked from Gateway, the crew fire their engine once to break out of the halo orbit, and once again to sling the spacecraft around the Moon, placing it on a multi-day trajectory back towards Earth. As they near the end of this journey, the service module is released, and the crew module is oriented heat shield first. Entering Earth's atmosphere at 25,000 miles per hour, the friction of air slows Orion considerably, while also subjecting it to temperatures of 5,000 degrees. With the Orion now at just 300 miles per hour, a series of parachutes uniquely tested and produced for this moment deploy, decelerating the craft to just 20 miles per hour for splashdown. With each successful mission, Artemis ushers in the next wave of men and women to explore our Moon and prove that together we are ready to go beyond.
The Moon. It's our nearest neighbor in space, and data we gather from its features can tell us a lot about the rest of our solar system. And through the eyes of the LRO spacecraft, we can explore the lunar surface in all new ways, in fascinating detail. Our tour begins on the western border, where the near side of the Moon meets the far side. The enormous feature is a lunar crater, and it's known as the Oriental Basin. Here, LRO's terrain map combines with surface gravity measurements from the Grail mission. This data reveals structure in the lunar crust beneath the surface, giving us a window into the geologic features of the Moon's interior. Our next location receives little direct sunlight and has some of the coldest recorded temperatures in the solar system, the South Pole. The highlighted spots signify potential water ice based on temperature readings from LRO's Diviner instrument and reflectance from its laser altimeter Lola. Lola also allows us to peer into the darkness of Shackleton Crater by bringing us this digital elevation model. It's 21 kilometers wide and 4 kilometers deep, but it pales in comparison to the largest known impact crater in the Earth-Moon system, the South Pole Aitken Basin. Sitting on the far side, it's 2,500 kilometers across and 13 kilometers deep. We don't yet know exactly how old the basin is, but it was first seen in the 1960s by spacecraft flying around the far side. As much as we use LRO data to investigate areas we can't see from Earth, we also probe familiar territory on the lunar near side to bring back images with an all-new level of detail. This is Tycho Crater. It's around 100 million years old. Here, the Lunar Reconnaissance Orbiter camera captures the central peak with a 100-meter wide boulder at the summit, the origins of which are still a mystery. Continuing across the Moon's near side, we will arrive in an area ripe for future exploration due to the diversity of impact and volcanic materials. It features a prominent crater so bright it's not only visible through telescopes, but also to the naked eye. Welcome to the Aristarchus Plateau. Here, infrared shows the mineral pyroxene in orange and a splash of plagioclase in blue from Aristarchus crater. This region can tell us a lot about the rich volcanic history of the Moon. As much as we study the Moon looking for sites to visit, we also look back at places we've already been. This is because the new data that LRO is gathering helps us reinterpret the geology of familiar places, giving scientists a better understanding of the sequence of events in early lunar history. Here, we descend to the Apollo 17 landing site in the Taurus-Littrow Valley, which is deeper than the Grand Canyon. The path the astronauts took over the course of 3 days is shown. The Lunar Reconnaissance Orbiter camera is even able to capture a view of the bottom half of the Apollo 17 lunar lander, which still sits on the surface, as well as the rover vehicle. These images help preserve our accomplishment of human exploration on the Moon's surface. Moving onward, we make our way to our final destination. This location contains regions that exist in permanent shadow, as well as ones that bask in nearly perpetual light. It's the North Pole. Detailed terrain measurements by Lola allow scientists to model sunlight and shadow at the poles over decades and centuries. Sunlit peaks and crater rims here may be ideal locations for generating solar power for future expeditions to the Moon. This updated visualization of the lunar landscape stands as a testament to the functionality and abilities of the Lunar Reconnaissance Orbiter spacecraft. And as the mission continues to gather data, it will provide us with many more opportunities to take a tour of our Moon.